First of all, I would like to thank to the organizers of this summer school. Really, they did hard work to make us very comfortable and to enable us working in very good condition. Thank you very much. The second, you will hear something different presentation. In fact, two of us will be the presenters. Professor Zdravković, Sunčica, she is now in England. I am here in Eger, so we shall see how is it going to work. This is in fact the experiment, but in the sense of the project. In fact, the project is visual mathematics and it is based on new technology, so we are using new technology and trying to be in the project all the time. And yesterday you heard a lot of visuality in mathematics, and in fact this is mathematical modeling, and now I'm going to tell you a little bit about this theoretical aspect of mathematical modeling. In the afternoon we shall work practice during the workshop. You will get material where we prepared a lot of things to be done as the mathematical modeling. The contents of this presentation, in fact, will be, of course, technology in education, mathematical model, mathematical modeling, modeling and technology in education, and of course, we are in Hungary. We have to mention George Polya. He is the person who is mostly seated in today's mathematical education. One example only, and of course, you will hear psychology in modeling by Professor Zdravković. So, first of all, I would like to tell you that I wrote some sentences and some noting. I cited it by authors because they told it better than I could tell it to you. I am speaking on English. So, let me say a little bit about David Toll. He is a very famous author in mathematical education now. And let me see first of all, mathematics begin from our perceptions and actions of natural world. This is our project, in fact. First, through practical mathematics, as we build on our perception of shape and space and our actions in counting, measuring that lead to the operations and so on. We use language, we are using language to describe objects and perform operations such as construction in geometry, counting, measuring, and so on, and more sophisticated operation in algebra, calculus, and other areas. Now, let's turn to our point, mathematical model. What is mathematical model? It can be say it is some kind of description of the system by using mathematics. I will not open this Wikipedia, you can do it by yourself. You have this presentation in your material, so you can do it. I am not doing now. And what is mathematical modeling? Mathematical modeling is the whole process that lead, they said, of developing mathematical model. Mathematical models are used in science, and sciences are used in mathematical modeling, so this is connected very well. Model is maybe help to explain some systems, therefore we are working some simulation and making models to explain some systems. We all know mathematicians and non-mathematicians, very well-known mathematical models, differential equation, dynamic system, statistic models, and so on. But now we are going to take care about mathematical modeling in education, because this is our point of view. And first of all, I would like to only list you few references. In our consideration, we are mostly taking care about the papers and the work of Professor Gloria Stillman. She is from Australia, and she spent, I think, 1 month or something like that in Serbia, in Belgrade and Novi Sad. And in fact, we got, after her visit, we start to work just mathematical modeling in scientific point of view. And these are also some other authors. Of course, we are working in Serbia in mathematical modeling. These are the papers listed on the end. So, mathematical modeling in education, in fact, there are some thinking that mathematical modeling had been applied long time ago. Yes, it is. But from this point of view, which we are now looking at, in fact, we are looking through the technology. It started in these mid-70s, 1970s, and this is the person who is thought as the first who did this. Mathematical modeling deals with process of creating models, we already told, that then should be applied in solving mathematical problems. There is no unique definition of mathematical models, of course, and mathematical models is obtained when we translate problem from everyday life to mathematics and then going back. Teaching and learning mathematical modeling with technology. In fact, this is the point, the most important point of our project, and in fact, explaining scientifically, this is in fact teaching and learning mathematical modeling with technology, and the approaches to teach mathematical modeling have been influenced by the development and introducing of technologies such as graphic calculator. Of course, the graphs of functions is in fact most models which we are using in our teaching, in our learning. Students are learning and using this graphic. And of course, I would like to point out the paper of Gloria Steelman. Also, you have it in your material. I will only say a few words. How is treating this theoretical process of mathematical modeling? In fact, she is taking care of this TRTLE. In fact, technology, rich teaching and learning environment affords new ways of enlarging students in learning mathematics. In fact, as we spoke, new technology influenced this new way of teaching. As we know, the presence of electronic technology in the classroom can fundamentally change how we think mathematically and what becomes privileged mathematical activity. So, we are taking care about interaction between mathematical modeling, mathematical contents, everything in mathematics, and technology. And I shall show you some graph. How does it look like? One part is technology, the other part is modeling and mathematical contents. And in fact, what are we doing? No, I cannot go because of technique, but I can explain. This yellow rectangular is in fact the point which we are working on. In fact, this is the intersection of mathematical modeling technology and mathematical contents. What is the first we can think about, but the authors agreed that the most important thing is in fact technology that is involved all this reasoning. So, and this is very simple. Before we met Professor Gloria Steelman, we in fact consider such a table as some kind of treating mathematical modeling. As you see, we start from real problem, formulate this problem, find mathematical model and go back. But now we are working much more in fact, and we have two PhD almost finished now in Novi Sad, PhD in mathematical modeling, and in fact they are in fact considering such kind of table a little bit change from their point of view and so on. As you can see, it is much more complicated. Of course, we have much more to speak about. So, we are starting from real situation, then we are going to real problem, real task, in fact, what we are asking to do. Then we are working some mathematics to get mathematical model. After that, we are working mathematically. We mathematicians are always working mathematically. So this work mathematics is in fact what we are teaching, what our students are learning, and so on. Everything else is a little bit new to be introduced. And then from mathematical solution, we are going to the solution of real problem. After that, we have to see what we get. You will see a lot of examples where we can accept the model or we cannot. Then we can go again and try something else. And what is the most important, because this is process of mathematical modeling which is used in all science, but in education, the most important are these transitions. For example, from real problem to mathematical models, because we have to think what we are going to do, what cognitive activities that we have to apply, the students have to apply to get some kind of knowledge to enlarge their knowledge. So, then, first of all, we shall, in fact, mostly, we are taking care about these two ellipses, say, connecting a real problem and mathematical model from one point of view, and from the other point of view, mathematical model and mathematical solution. And to see cognitive activities, now we shall list it, and then we shall connect it with what George Polya say about this cognitive activity. In fact, I didn't tell correctly. We implement Polya's work in this mathematical modeling because this is, of course, newest thing than when he worked, but it can be implemented very well, and we are working. So, going from real problem to mathematical modeling, we have to do a lot of cognitive activities to understand the problem, to simplify the problem, to interpret what this context means, to do some mathematics, in fact. Also, from mathematical model to mathematical solution, as I already told, we are working all the time, we are working mathematics. We are just doing all activity to solve our problem. And also, then we have to connect, to transit. If we get mathematical solution, to get the solution of real problem. When we get the solution of real problem, we have to discuss, can we accept or not. In fact, if we have some points, if we fit curve, and then this means that we can get some function. This function we can to see what is going to be to do, why we did it, and so on. So therefore, we have to discuss about the obtained mathematical model. If it is okay, we accept and write a report, of course. If it is not, then we are going back again. What can we do? And in fact, this is the explanation interpreting mathematical outputs and comparing, criticize, validating, and so on. And now, let's say a little bit about Professor George Polya. He is Hungarian, and this is a little bit written about him. And in fact, besides, he worked a lot in mathematical education, but besides, of course, he worked in other field of mathematics, combinatorics, number theory, numerical analysis, and probabilistic theory. And now we are going back to his educational work. In fact, he wrote 4 books, which are very interesting for us, and I think almost on each our seminar or everything else, we were speaking about, I think this book, How to Solve It, this is the most popular, I think, book, but also there are these other 3, Mathematical Discovery, Mathematics and Placeable Reasoning, Volume 1 and Volume 2, Volume 1 and Volume 2. So, and Mathematical Discovery, so these are these 4 books of George Polya. This book, How to Solve It, in fact, has a very good explanations and very good explanations, a lot of things in mathematical modeling, in mathematical education. For example, I point out few sentences from his work. For example, what is good education? Means systematically given opportunity to the students to discover things by himself. What advice? This is education at all. Wise advice. What you can if you cannot solve the problem, Then there is an easier problem that you can solve it and try to find it. Now, he was a mathematician, and of course, the point is in mathematical education, and this is interesting. Mathematical is good school of thinking. Really it is. When we are speaking about mathematics, each time we don't say we are learning mathematics. We are working, we are doing mathematics. And in fact, this doing mathematics forces us to think mathematically. This mathematical thinking, a lot of authors are taking care of this mathematical thinking, and this is in fact the point. But what is thinking? The thinking that you can learn in mathematics is, for instance, handled with abstractions. That's the most important. Mathematics is about the numbers. Numbers are an abstraction. When we solve a practical problem, then from this practical problem, we must first make an abstraction problem. But I think there is one point which is even more important. Mathematical, you see, is not a spectacular sport. To understand mathematics means to be able to do mathematics, what I told you. When you say you are doing mathematics, you are not learning. And what does that mean, doing mathematics? In the first place, it means to be able to solve mathematical problems. Of course, we all know this, but this is, he said better than I could, therefore I took his sentences. And I like this, his sentence very much. Teaching is not a science, it is an art. Really, it is an art. And he explained, if it would be a science, then that would be the best way of teaching, and everyone would have to teach like that. For example, Pythagoras theorem is Pythagoras theorem, and that's it. You cannot do any research, anything else. I think that Pythagoras theorem should do like this and this. So this is science, and teaching is in fact an art, and we have to I don't know what is Christo going to say, but George Polya is treating it as an art. Since teaching is not a science, there is a great latitude and much possibility for personal differences. Everybody is teaching on his own way. Of course, we know that, and therefore we are having, that's the reason that we are having this project, to make some together activities in our further work, and also our students to see how to work further. You agree? I'm happy. Okay. Perhaps the first point, which is widely expected, is that teacher must be active or rather active learning, and therefore we are working mathematical modeling to be active during our teaching and learning, and we are on that point of view doing our visuality. So the most important 4 steps in problem solving, mean George Polya consideration, is these 4 steps: understanding the problem, devising a plan of solving problem, carrying out the problem, and going back. And in fact, what are we doing? We are include all these things in our mathematical modeling process. Sorry. So first, what does that mean, understanding the problem? Everybody knows. I pointed here to a few things of what does that mean, understanding the problem. But in fact, this also means when we start from real problem to mathematical model, we have to understand the problem. That's the most important thing. Further on, devising a plan. Of course, if we understand, we can make some plan how to solve the problem. And we are working, when we are just working mathematics, or we can do it in mathematical modeling process. It will be shown later. Carrying out the plan, of course, we have to finish our work. We have to do this. That's normally. I wrote it few sentences how to be explained. And then looking back, we were speaking about looking back in mathematical modeling. Also, Professor Polya told us that we have to take care to go back and to see what did we do. So, as I told, of course, we mentioned Professor Polya in the sense of our mathematical modeling process. So, in that case, in fact, Professor Polja, in fact, has his, how to say, turns out to these cognitive activities. First of all, from a real problem to mathematical model, and from mathematical model to mathematical solution. And in fact, we can apply all the mentioned 4 steps, which we mentioned before, to this. These are in fact this cognitive activity, but told in the sense of mathematical modeling process. So these are cognitive activities. We are starting from real problem, going to mathematical model, then mathematical solution, and real solution. And as I told, we have to understand the problem, but in fact, we cannot divide. We cannot divide in to say, for example, from real problem to mathematical model, this is only understanding. No, all 4 activities and cognitive activities has to be applied in all 4 transitions, from real problem to mathematical model. We have to understand, we have to devise a plan, to carry out the plan, to obtain what we need, and also to go back. Maybe looking back can be go to the other, but we have to go back to see what we get. And the same thing is this transition. So the most important things in mathematical modeling, in education, we are taking care about these cognitive activities. Model is model. We suppose that we are mathematicians, the model will be good or bad. We shall discuss about that. But in treating in mathematical education, we are treating modeling cognitive activity applied in mathematical modeling. And so, before we start with the example, I shall include Professor Sunčica Zdravković. In fact, now we shall give an example starting from forgetting, from the psychology, from real situation, going from psychology. And first of all, Professor Zdravković will tell you about Hermann Ebbinghaus, about memory function, and then we shall go on about on this example to explain the whole mathematical modeling process. No. Yes, you are right. Okay.
Hello?
Hello.
Better?
Yes, better.
Okay, let me just
bolje.
show you presentation. Kako? A, dobro, hvala.
Učvrstite glavu.
Učvrsti glavu, priđi na jedno mesto, samo lagano priči i bit će okej.
Is this good?
Yes.
Okay. So basically, as I said, in science, we are using mathematics to describe phenomena that we are studying. And mathematical modeling help us describe those phenomena in a very precise language. In the field I'm working, which is psychology and neuroscience, first of all, we use statistics to model the phenomena we're working with. And we mostly use 2 types of statistics. Statistics that I'm sure you are all very familiar with. Like 30% of the people learn really fast. Okay. But we also, in psychology and social sciences, very often use something called Bayesian statistics. As I'm sure all the mathematicians in the audience are very familiar with this, maybe other people in the audience who are not so familiar with mathematics maybe do not know about Bayesian statistics. The idea of these statistics is actually very, very close to what we need in social sciences. And this would be, let's take an easy example from meteorology. And we say on July 16, that is tomorrow, the weather in Eger is going to be very nice. Because last 100 years, when we measured the weather in Eger on July 16, it was always about 26 degrees. So we are concluding that based on frequency statistics, tomorrow will also be 26 or about 26 degrees. However, if we use Bayesian statistics, then we know that there is only one tomorrow in the whole universe and time. There is only one July 16, 2014. And whatever happens before really have nothing to do with tomorrow's weather. And for this, we use way more complex distributions that do not only count what was the weather like 100 years ago, but include the weather of today, of yesterday, and some other things. So basically, when we want to infer who's going to win next elections, we don't just see who won last 100 years in the elections, but there are only one elections this year in your country, and they require Bayesian statistics for much better predictions. And then different statistical models to base model psychology and neuroscience. We use different neural networks of swarm intelligence and so forth. Now, modeling cognitive functions is a really old thing in psychology. It's going on for around 2 centuries. And my students in psychology are sometimes amazed when I tell them this. When you say mathematical model, they imagine something extremely complex. But as I'm going to show you how mathematical models can be extremely, extremely simple. Just the one I'm going to show you, which is about 150 years old. It's from the end of 19th century. And it has to do with the famous scientist called Hermann Ebbinghaus, who lived between 1850 and 1909. And he was working on memory. This is his very famous book. And he actually to see how the human memory works. What can we learn? How fast can we learn? How fast we memorize and how fast we forget. And he decided to do something that was very different from the zeitgeist in which he lived. So he decided to employ an experimental study. So basically the idea was that he would start memorizing words and then repeat and measure how many words he memorized within an hour, after 2 hours, after 3 hours, 3 days, and so forth. And being very, very neat and peculiar man, he actually came up with an absolutely magnificent methodology in which first he decided that you cannot learn just N words, because some people might remember something because they are familiar with the topic, or because they find something interesting, or because they knew something about it from before. So he says, okay, let's learn nonsensible syllables. They will give us a perfect material where no other cognitive functions can apply to. So this means basically you would take one consonant, one vowel, one consonant, and make a syllabus out of it. For example, B-O-L, and you end up with the syllabus ball. Now, you may not, if you are an English speaker, use this one because it resembles a well-known word. But if you use D-A-X, ducks, that would be a perfect example because it doesn't mean anything in English. And he came up with a huge collection of these nonsensible words that he would use, and then he would, at the sound of metronome, he would put them in the box, and he would start taking one after another from the box, and then would read them and memorize them, and would actually ask himself in a systematic intervals to write down in the notebook which one of them he can remember. One investigation included 15,000 recitations. This research he led on himself on daily basis for about 10 years. I mean, talking about actual scientific devotion to a project. And he ended up with something we call today forgetting curve, and that is something that you will model right now with Professor Durdica. So this curve describes the exponential loss of information that one has learned. So as already you can see when I tell you this, and if you are a mathematician or if you have any even small training, when I tell you that the forgetful is exponential loss, you all know something about functions, cognitive functions. And the curve levels off after about 1 day, so it has asymptotic loss after 1 day. So these are all mathematical language used to precisely describe this cognitive function, forgetting. The learning curve is basically the same curve, just in an opposite direction, and it refers how fast one learns information. Another thing that Ebbinghaus found was a position effect, meaning that words learned at the beginning, at the end, and at the end of the sentence has a particular place in memorizing. So basically, the first position comes for the things that were learned in the middle, while the things learned at the beginning and at the very end, let's say, of your talk, of your presentation, of your class, have much better position in learning. So this is a very good thing if you are a teacher. If you want to say things that are important, make the beginning of your class an abstract form of what you intend to say, so that people memorize the overview. And make the end of your talk something they called take-home messages, where you would actually summarize the answers of the things. That way, your audience will prospect most of your lesson. And this is what Ebbinghaus found out. If he's immediately recalling the nonsensical words was learning, he would be able to recall 100% of what he was learning. The amount of recall is given on y-axis, while the time between the learning and the recall is given on x. In psychological experiments, this is a typical way to report the experimental data. On x-axis, you would present something varied. In this case, Ebbinghaus varied the time between the learning and the recall, so elapsed time in days. On the y-axis, you would have whatever you are measuring, in this case, percentage of the material that he could remember. So as you see, as time goes by, we have this exponential loss of information, or exponential loss of amount of things, percentage of things he could remember. And as I said, after a day, the effect wears off, and we end up with this asymptotic, so it never goes all the way to zero, but it asymptotes about 20% of the material that he learned.
So, can I continue a little bit, and then we shall come back to you?
Now it's your turn.
Thank you. So, we see how does it look like? Real situation. I did it really by purpose to here, because real situation comes not from mathematicians, and you hear how does it look like when non-mathematician is speaking about that. So our to say task as a mathematical teacher is now to choose, that was real situation what Professor Zdravković is speaking about us, and now we are going to real problem. What is real problem for us? Real problem for us is to visualize this forgetting material or something like that, or forgetting or left material. So, we have a problem. The problem is the following. We know, it is known, Ebbinghaus has some notes, of course, where he told that after 20 minutes, a person forgets, say, 58.2. But this is what was Professor Zdravković speaking about. This is 58 some percent or something like that. That you cannot say, this is not, you know, that you can say exactly. Therefore, you have this, I would say this is some fuzzy, or therefore they are working some statistics, some round. It depends of the contents, of the person, of the time, of a lot of things are influence of this. And we, mathematicians, are taking like this, or we are taking what is much more better here. After 20 minutes, one forgets 40% of material. This is 40% now, and we shall treat it now at the beginning as 40%. I think that we shall make something with Professor Zdravković a little bit we shall work something more about considering these, in fact, cognitive curves and cognitive, in fact, this was now very short time to make something like that. So, this looks like our real problem. And it is psychological problem. I rewrite it from psychological book for 2nd grade or something like that. This looks like this. Of course, we know that this is not exactly, and that's it. So, we have to make mathematics of this. This is now psychology, and now we are going to mathematics. And then, what we have to do? We have to see how to make curve representing this. What are we going to represent? The contents which are left or the contents which you forget. This is how to say, this is the thing. Let's go back to Ebbinghaus curve. What does that mean? He consider, you see, he consider, I think, the left material, not forgotten material, is it? Because after he, person lost 60% of his, or 60% stay, and 50 and 40% loss. So it depends what is, and Sunčica was also speaking about, what is going to be dependent variable, what is going to be independent variable. And these are all these cognitive activities which we can to take care about and how to present it with graphs. If we look here, it is presented by lines. He just make lines, connected points with lines, and that is it. This is in fact logarithmic curve, but never mind that this is inverse to exponential, so he is treating as exponential, no problem. And then let's go back. So in our mathematical modeling, we are taking care about all these cognitive activities. So we are trying to fit curve corresponding. Now it is very well known and very easy to be done. When I start my teaching, then this fitting curve, I was working with my students whole 3 hours, probably some remember as well. Now, when we work numerical analysis, we have to write everything. Now, we have to click something and go to the whole curve, which is the best fitting to all these points which we obtain. And we can do it in our workshop if somebody is interested. You have it in your material prepared. And now also we have to go from real problem to mathematical model. Now this is our, how to say, to make mathematics of this psychological thing. So we have to make graph. We use GeoGebra for that person, but we can use any other program which we know to work. When we get this curve, we have to write equation to examine the graph, to see what we get, of course. What does that mean? And to compare with the given graph by Ebbinghaus. And in fact, this looks like our fitting curve. You see, it is very much look like Ebbinghaus curve. And this is the equation of this curve which we obtain. And we can play also. With GeoGebra, we can move the point A, B, C, D. And so we can have, how does it, this is called consistence of when we are considering equation and changing coefficients, how does it look like? Now we are changing the coordinates of the point and to follow how the curve is working. There are a lot of programs made, but not in GeoGebra. I think in Mathematica and in MATLAB, of course, they have a lot of programs for this cognitive curve, so it can be done, but now we did not do. So this is mathematical model. This curve and this equation is mathematical model. Now we have to speak about this mathematical model. This is, we implemented the strategies from previous and present the graph, but we need to analyze, as I told, mathematical model and to see what we get, to see what is real solution. To go back, looking back, what we consider forgotten or left material, to analyze what is it going in between, say, we have after 20 minutes, after 9 hours, after 2 days, what is going to be after 15 days or something like that, or later and so on. And we can see that this is, in fact, it has horizontal asymptote. We know what, we mathematically know what does that mean. But in fact, for also the psychology people also we speak about this asymptotically behaving. So we are somewhere together. So we are speaking more or less the same word. So this is different analysis. And then we can see, I made another graph This graph represents forgotten material. The previous graph means left material, and this is forgotten material. What is nice for us mathematicians? For us mathematicians, these graphs can tell us much more about forgetting than the previous. Why? Because when you consider, for example, here, you can follow the speed of forgetting. The speed, you can make tangent line, and you can speak about the speed. And you can see at the beginning, the speed is bigger, the tangent of angle. If angle is bigger, the tangent is bigger. If angle, so we can follow the speed. We can make differential equations. We can work a lot of mathematics in this forgetting curve. Not only, of course, we are mathematicians, and we as teachers have to prepare our students, or it depends on the level. If they are low, say, second degree, when they are working exponential function, in that case we cannot work with differential equation with the speed. But when we are working at the university, we can speak about the speed, about velocity, about a lot of things we can see about this. So this is a differential equation. In fact, the whole problem we can make considering this. This problem, different analysis, comparing the graphs. This is one graph, so forgotten material. The other, I think Sunčica mentioned in some time these graphs of forgotten and left material. And as I told, the first derivative can be compared, conclusions can be seen better from the for us mathematicians, but for them. And that is very interesting when we work together. And when she said on her words, and then I interpret on my mathematical words, and this is our project, why it is interesting. And so we shall ask Professor Zdravković to speak us. Please, can you continue?
Do we jump to visual illusions now, or do we want to model the distributions?
About illusions, please. We have, yes, please.
Okay.
10 minutes. You have 10 minutes. Ali mogu ja malo, vi sad koliko hoćete, ja ću posle onda sa GeoGebrom malo prilagoditi se.
So, I will continue about visual illusions, which is something you need to know about for your workshops.
Radit ćemo u workshopu
This time,
iluzije, pa onda.
we will not model the cognitive functions you did last time in-house, but we will try to model what the information the system is taking in. So let me tell you about visual illusions. There are amazing phenomena of normal vision. So normal people, normal vision, people with normal vision experience visual illusions. Let me show you some of them. On one side, you see the Ebbinghaus illusion. This is the same Ebbinghaus from before. Those two red balls in the middle are of the same size. On the other side, you see illusion by Gregory. And these tiles of black and white squares are in fact parallel. Now, these are quite powerful illusions, and hopefully you're familiar with most of the things I'm going to show you. It's only when you somehow discard the context, you can see the realistic situation of the physical stimuli. For example, if I put the red lines, or if I get rid of the surrounding balls, you can see the two red balls are the same, and maybe you can see that our tiles are in fact parallel. However, these illusions are so powerful that your knowledge of the real situation of the physical stimuli really doesn't help you not to see these illusions. You see these powerful illusions in any case. So, these are perceived images that give objective reality. And it will be interesting for us in this book are so-called geometrical optical illusions. There are distortion of size, length, position. In the two illusions I just showed you, there was this distortion of size and distortion of position. The reason for this illusion is the perceptual organization. So every time you have physical reality, your perceptual system tries to build up percepts, basically some kind of a model, internal model. Now, not a mathematical model, but mental model of what is going on in the world. And sometimes it implies really strange solution. So basically, I'm sure all of you can see on this image a white rectangle, also known as Kanica triangle. Oh, sorry, not rectangle, triangle. A white triangle that is superimposed on a black outline of a triangle and the three circles. However, really, there is no white triangle in this picture. This is the consequence of perceptual organization, our mental models that our cognitive system applies. And these kind of models create visual illusion. So this is basically to leave the effect of context. So when I show you two lines of the same length, just like that, you would see that they are the same size. As soon as I add the context, like this famous Miller-Lire illusion, the line that is at the bottom starts appearing shorter than the line on the top. This illusion doesn't work just as one-dimensional objects like lines. It also works with other objects. Here, I make the context even richer. So apart from those two errors on the side, I have some perspective effect. So the line on the bottom appears even shorter than it did a minute ago before I introduced richer context. As I said, this works with two-dimensional objects as well, like circles. So if you have two circles that are the same size, and I move one into perspective, it starts to appear larger already. If I surround it, like in Ebbinghaus illusion with other objects, then you can no longer see these two circles as being of the same size. Do you agree? Can you see what I'm showing?
Da, vidimo.
Okay. Now, it works for three-dimensional objects as well. Here is a three-dimensional object, and here is a one of the same physical size that doesn't appear so. So these are so far illusion of size and volume, but you get the same illusion in the domain of colors. So basically, can you see the pointer that I'm showing now? Can you see the arrow?
Yes.
Yes?
Yes.
Okay. This circle here is made of the same color as the circle here. Right? So these are the illusions. They are as powerful as the illusion. So this is the same color here. Okay. The most famous illusion color is simultaneous contrast. Look at these gray circles here. They are the targets. Now, when I start changing the background of these targets, you will experience a very powerful simultaneous lightness contrast illusion. I urge you to look at this circle here because it will go through the largest change. So remember, these circles, as you can see them now without the context, are actually the same gray shade. As soon as I start introducing context, it is changing before your eyes. Did you see that? So look, they're actually the same. And just as I said, your knowledge really doesn't help you to overcome a visual illusion. Whatever comes as an input, perceptually, seems to override your knowledge about things. And we actually, in psychology, explore this illusion a lot, and there are numbers of papers that are written about this. So the illusion is written both on paper and on a computer screen. The changes were made in color or illumination, color of targets, color of background. A lot of different things was done with this illusion, so that we know precisely when and how this illusion influenced the visual system. This illusion also works in color. If you have two identical orange targets, they would change as soon as you add different backgrounds. Okay, now I will show you another very powerful illusion. I want you to stare at the box in the middle of this colorful image. Now, what I need you to do for a few seconds is moving your head. Stop talking to each other and just really, without moving, stare at the cross in the middle. Can you do that? Just stop doing anything for a few seconds it is crucial that you don't move your heads, that you don't move your gaze from the cross. Just keep staring. It is really, really beautiful if you can make yourself just stare a few seconds. It doesn't take long, and I'm trying to chat you up so that this really works well, but it is important to stare and stare and stare at the cross, and then, did you see the effect?
Nothing. Why?
Okay. Can somebody talk, please?
That's only white. Samo je beli
Can
pravougalan.
anybody see the effect?
To tako treba.
So I'm showing you.
Da. Sad ništa, sad je beli samo pravougalan. Ne vidimo ništa.
Profesorka.
Molim, ne vidi se ništa, samo beli pravougaonik. A onda se videlo ono 4 šarena.
No. I need the audience who actually stared at this to tell me did they experience the after effect. Christoph, can you nod your head?
Kažu da je to tako i treba.
Okay, let me go on. So basically, the illusory effect get either from illumination. So basically, if you have two gray squares, and one is in the shadow and another is not, and you have two identical shades with two backgrounds, just like we've seen in these illusions. So the amount of light coming from these two exactly the same targets, which in physics we call luminance, is equal. In this case, when we have shadow, it's no longer equal. The way we model shadow is multiplication. So when you add shadow or a spotlight, you multiply the level of luminance with the intensity of the light. So in case of the shadow, it is luminance through the intensity of the shadow. This is for mathematical things. Now, what is the
Aha, sad je malo, imamo izgleda problema. Hoćete malo, možda i da završite. Da. Da, nešto. Ovdje. Eto, this is technique. But you can hear, we can heard it, okay? And I did it by purpose. Yesterday you heard Professor Jablan. He was speaking about illusion, and now we can on the workshop work some of these illusions.
Okay, let me just show you the last.
We have problem, but we still have had enough to hear her. Okay, no problem. I can continue. Okay, Sunčice, nema veze. Ja ću nastaviti. So, we were lucky. 18 minutes, that's okay. So, we shall speak with Sunčica later. No problem. No, that's okay. We shall not. No problem. So, I would like to finish with this mathematical modeling. Sunčica is going to say goodbye. Yes, she. Answer. Jel nas sad čujete?
Yes, I can hear you very well. Can you hear me?
Da, pa da završimo. Sad je već vreme. Vi se pozdravite, pa može?
Yes. Okay, let me show you the way we actually employ these illusions, and you are going to model some of these things later in your workshops. So basically, we can see the same gray targets here. As soon as we introduce a little bit of context, they still appear relatively same. We introduce a little bit of more context, and we get the illusion that is equal to the change of the background. Now, when we introduce more of the context, they start looking very different. And if we actually add both effects of the background on the end of illumination, we get a very powerful illusion. So let me remind you, we start from the identical gray targets. We add the background, and the changes are already significant. We add illumination, and the changes are huge. And in psychology, we actually found a way to model some of these effects and cognitive functions. But in this course, which you're going to do in your workshops in the next few days, you will be modeling the illusions itself, not the cognitive functions like it is shown here. Thank you very much for your attention, and I wish you a very nice and pleasant stay in the summer school, and thank everybody for actually having patience to organize my appearance in this talk. All the best and goodbye.
Thank you also very much.